So let's just jump into this first example. Here I have two restaurants, Olive Garden and Cheesecake Factory, and I have wait times at each of these restaurants. Part A says find the mean wait time at each restaurant. So I know you know how to find the mean. Just add up the data values and then divide by however many data values you have. So in this case, it's 1, 2, 3, 4, 5. So we'll add this up and then divide by 5. So I'm just going to tell you what the mean is. So for Olive Garden, the mean is 61. If you do the same thing for the Cheesecake Factory wait times, I'll tell you that the Cheesecake Factory mean is also 61. So what does this mean? Does this mean that the wait times at the two restaurants are about the same? No, not quite. Right? If you look at the actual wait times, there's something else going on here that might be important to you. Right? If you look at the Olive Garden wait times, they're all close together. They're all kind of close to 60-ish minutes. Right? So about an hour wait at Olive Garden. At Cheesecake Factory, the wait times are more all over the place, right? Could be as low as 33 minutes, or it could be as high as 90 minutes, an hour and a half. So looking at the mean alone doesn't tell you the full story of the data. And even looking at the median alone doesn't tell you the full story of the data. The data is already in order, so the middle number here is 61. The middle number on a Cheesecake Factory is 57, so 61, 57, also about the same, right? So if we just look at measures of center, which is like mean and median, it doesn't tell us the full story of the data. Right? So today we're going to talk about measures of spread. So these are numbers that tell us something about how spread out the data is. And then just to answer part B, what restaurant's wait time appears more spread out? Cheesecake Factory. The first measure of spread we'll talk about is a very simple one called the range. The range is just the biggest number minus the smallest number. I'll write it as the max minus the minimum. So part A, find a range for Olive Garden. So the biggest number for Olive Garden was 67. The smallest number was 57, so 67 minus 57. And it's 10. Find a range for Cheesecake Factory. So the biggest, the max for Cheesecake Factory was 90. The minimum for Cheesecake Factory was 33. So 90 minus 33. Okay, what's 90 minus 33? 57. So like we said, the 57 Cheesecake Factory was more spread out than Olive Garden. Because the range is so easy to calculate, you just take the biggest number minus the smallest number. It's also not very useful. The more useful measure of spread is going to be the standard deviation. What I want to do here is give you an idea of what the standard deviation is. So I'm going to start here by I'm going to calculate standard deviation for the Olive Garden numbers. Okay, so let me first copy down the Olive Garden numbers. 57, 57, 61, 63, and 67. And what I'm going to do here is do exactly what we did in the previous lecture, which is find the deviations from the mean. The mean here was, we said the mean was 61. Okay, so we're going to find the deviations from 61. And remember, deviations is just the distance from 61. So how far is 57 from 61? It's 4 below, so it'll be -4. And remember, if you can't eyeball it, just subtract, right? So 57 minus 61 is negative 4. 57 minus 61 is another negative 4. 61 minus 61 is 0. 63 minus 61 is a positive 2. And then 67 minus 61 is a positive 6. Okay, so we have the deviations from the mean. Now, the idea behind standard deviation is, what I want to do is find the average of the deviations. So I would like to find the average of these deviations, which means to do what? Add them up and then divide by 1, 2, 3, 4, 5. But what's the problem here? What do you get when you add these up? What do you always get when you add up the deviations from the mean? From the last lecture, when you add up the deviations from the mean, you're always going to get 0, right? So if I add these up, I get 0, and then I divide by 5, I get 0, which is not very useful, right? Because I don't want to always get 0 as my answer. So I can't just take the average of the deviations. And then the problem here is that what always happens is that the negative deviations are going to cancel out the positive deviations, and you're always going to get 0. So what do? Well, I want to do something to get rid of these negative numbers. So from your algebra class, what could I do to turn a negative number into a positive number? I'm thinking of two things that you might be thinking of. If you said take the absolute value, that's good. That's not what we're going to do, but that's good. So outside of absolute value, what's another thing you can do to turn a negative number into a positive number? We're going to square them. Okay? So I'm going to take all my deviations and square them. So negative 4 squared, which just means negative 4 times negative 4. So negative 4 times negative 4 is going to be a positive 16. Negative 4 times negative 4 again, positive 16. 0 squared, 0. 2 squared, that's 2 times 2, 4. 6 squared, that's 6 times 6, is 36. So the idea here now is, instead of taking the average of the regular deviations, since I'm always going to get 0, instead of taking the average of the regular deviations, I'm going to take the average of the deviations squared. Okay, so what does that mean? That means add these up. Add those up and then divide by 1, 2, 3, 4, 5. Okay, so let's see what we get. Up top, 16 plus 16 plus 0 plus 4 plus 36 is 72. And then 72 divided by 5 is 14.4. Now, I'm not done, okay? Remember, what I really wanted was the average of the regular deviations. But instead, I squared them, and then I took the average. So what I want to do now is, how do I get rid of the square? So in algebra, if you have something that's squared, how do you undo a square? You take the square root, okay? And that's exactly what I'm going to do next. So take the square root of 14.4. So square root of 14.4. And then I'll round to three decimal places here. So that's 3.7. 0.95. Okay, and that's the idea behind standard deviation. Now, going back to where I said there's two algebra ways to turn a negative number into a positive number. Now, there is another approach to a standard deviation type thing where instead of squaring it, you take the absolute value. Okay, so that's not what we're going to talk about in this class, but if you're interested in that, you should take a more advanced statistics class, sort of like the next class that comes after this class. For everything we talk about in this class, there's usually a population version and a sample version, right? If you do the calculation on everybody in the population, it's going to be the population version. If you do the calculation on a smaller subcollection, it's called the sample version. Let me start off with the mean, since we talked about this already. If you calculate the mean using data from everybody in the population, the symbol is mu. So that's the Greek letter mu. If you did the calculation on a smaller subcollection, the symbol is x bar. For standard deviation, if you do the calculation on everybody in the population, the symbol is sigma, so that's the Greek letter sigma. If you did it on a sample, it's a lowercase s. Number of data values. If you're talking about the population, it's capital N. If you're talking about a sample, it's lowercase n. Variance, which we won't talk about very much. Variance is just standard deviation squared. So for the population, you take the standard deviation for the population, and then you just square it. For the sample version, you take the standard deviation for the sample, and then square that. And remember, the idea behind statistics is what we really want are all of these population numbers, right? But reality is you can't get data from everybody in the population. There's just too many. So instead, you have these numbers. And the idea here is if you do things correctly, the sample numbers should be pretty close to the population numbers. Okay? All right, so now let's talk about the official formulas for standard deviation. Okay, so we have a population version, and then we have a sample version. So let me start off with the population version. Okay, what's this big equation mean? Okay, so let me start with this x. So this x is your data. And what is this x? What is this formula telling you to do? It says take your data, subtract this. What is this? The mean, right? So this is saying take your data and subtract the mean. Okay? And then square it. So let's go back to when we talked about the idea. Taking your data, subtract the mean. Okay? We did that, right? We took our data, subtract 61, the mean, and what do you get? You get this -4. So your data minus the mean is this number, which is just the deviations, right? Data minus the mean is just your deviations. And then square it, okay? Which is also what we did, right? We took our deviations and we squared them. What's this symbol? This is a sigma. It means add up this. So add up your deviation squared. And then divide by n. So n is, remember, the number of data values. So n is number data values, which is exactly what we did, right? That just means take the average of the deviation squared, right? So we add up the deviation squared, and then we divide it by the number of data values, and there were 5 of them. So that's what that's telling you to do. Add up your deviation squared and divide by the number of data values. And then the very last step was take the square root. Take the square root. So this equation, this formula is telling you to do exactly what we did on the previous page, right? So what we did on the previous page was really the population standard deviation. Now, let's look at the sample standard deviation. What this x, right, still means data. It says take your data, subtract x bar. What's x bar? The mean. So this is telling you to do, for the sample standard deviation, to also do the same thing. Take your data, subtract the mean, and then square it, and then add it up. The only difference is here, you're dividing by the number of data values. Here, you're dividing by number of data values minus 1. Why is that? Remember, the idea here is I want the sample number to be a good approximation to the population number. And so it turns out if you just put an n there, regular n, without the minus 1, it turns out that you don't get a good approximation. The answer you get is usually always too small. So to adjust for that, if you replace it with n minus 1 instead of n, you do get a good approximation, right? The sample number is a good approximation to the population number. Okay, so that's the only difference. When you go to the divide step, if we're talking about sample, you divide by 1 less. Okay, so let me go back to this previous page. So since we divided by the full 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, what we calculated here was the population standard deviation. Okay. So most of the time, we're not going to calculate the population standard deviation because most of the time, we don't have data from the entire population, which means most of the time, you're not going to be doing what we did on the previous page. Okay. And then the formulas for variance, which I don't want to talk about very much, but the only difference is the variance formulas don't have a square root. So the variance is really just the number that you get before you take the square root. So if I go back to my previous page, the number that we get before we took the square root was this 14.4. Right, so that's the variance. So this is the population variance. Let's now use these formulas to find the standard deviation. Example 1. Find the sample standard deviation for the following data set. Remember, there's two types of standard deviations. There's a population version, and then there's a sample version. Here, we're looking for the sample version. And there's two different formulas. So which formula am I going to use? The left one or the right one? The sample version, right? So this one. Let me recopy this. Okay. So what this formula is telling me to do is the x is our data. The x bar, this is the mean. The n, little n, this is the number of data values. Okay, so this is saying take each of the data and subtract it by the mean. So I'm going to make a table here to organize my calculations. Okay, so I'm going to first list my x's, my data. So my data is 24, 27, 13, 53, 47, and 52. Okay. The first thing this is telling me to do is take each of my data and subtract it by x bar, which is the mean. Do I know the mean right now? No, not yet, right? So I do have to find the mean first. And to find the mean, remember, you're going to add up everything. So that's 24 plus 27 plus 13 plus 53 plus 47 plus 52. And then divide by however many data values you have. So 1, 2, 3, 4, 5, 6. All right, so up top, 24 plus 27 plus 13 plus 53 plus 47 plus 52. That's 216. 216 divided by 6. And it's 36. Okay, so now take our data and subtract it by the mean, which is 36 now. Okay, so 24 minus 36, negative 12. 27 minus 36, negative 9. 13 minus 36, negative 23. 53 minus 36, 17. 47 minus 36, 11. 52 minus 36, 16. Okay. So remember, whenever you take the data and subtract it the mean, that's really just the deviations, right? So this is just a complicated way of saying find the deviations. So we just did x minus x bar. The next thing is square our answers. Okay, take x minus x bar. In other words, take the deviations and square them. So negative 12 squared. That's a negative 12 times negative 12. Positive 144. And you're always going to get positive. Remember, that's the idea of squaring it, was to get rid of these negatives, right? Next up is negative 9 squared. Negative 9 times negative 9, I know, is 81. Negative 23 squared, so negative 23 times negative 23, positive 529. 17 squared, 289. 11 squared, I think it's 121. 16 squared, 256. Okay, so we did the square. The next thing is this symbol, which means add up that column. So we're going to add up this column. So 144 plus 81 plus 529 plus 289 plus 121 plus 256. 1420. Next up, divide that by n minus 1. Okay, so we're going to take 1420 and divide it by the number of data values minus 1. Number of data values is 1, 2, 3, 4, 5, 6. So we're going to divide it by 6 minus 1. Okay, remember, this is the difference between the sample version and the population version. The sample version, you divide it by the number of data values minus 1. The population version, you divide it by the 6. So there's not a minus 1. Okay, so we're going to do 1420 divided by 5. So 1420 divided by 5 is 284. And then one last step. Okay, very last step is this symbol, which means take the square root. So square root 284 is and then I'm going to round to 3 decimal places like we always do. So 16.852. Okay, and that is the sample standard deviation. So sample standard deviation. Okay, the number that you get before you took the square root, that's called the sample variance. Which I won't talk about too much. Okay, so we found the sample standard deviation by hand. I'm going to ask you to do it one more time on the lab, and then that's it. And then after that, we'll do it by using a computer. Why do we care about the standard deviation? We care because there's something called the empirical rule. Okay, so before I talk about the empirical rule, let's read example 2 real quick. Example 2 says the systolic blood pressure of 18-year-old women is normally distributed with mean 120 and standard deviation 12. Normally distributed means the data looks like this picture. Okay, so I'm going to label this picture. We're going to put the mean in the middle. So the mean here is 120. In the middle will be right here. And then we're going to use the standard deviation to go up, okay, 3 times. So 120 plus the standard deviation. So 120 plus 12 is 132. Plus 12 again is 144. Plus 12 one more time is 156. Okay, and then we're going to do the same thing, except we're going to go down. So 120 minus 12 is 108. Minus 12 again, so 108 minus 12. It's 96. And then minus 12 one more time is 84. Okay, so we label this picture by putting the mean in the middle and then using the standard deviation to go up 3 times and down 3 times. Now, the empirical rule says, so the empirical rule is sometimes called the 68, 95, 99.7 rule. And what it says is, for any data that looks like this, if you draw this picture, then 68% of your data is going to be between 1 up and 1 down from the mean. So here's the mean. 1 up, 1 down would be from 108 to 132. And that should be 68% of your data. 2 up, 2 down is 95% of your data. 3 up, 3 down is 99.7% of your data. And then I'm going to add one more number, which is everything. So everything. So all the way to the left, all the way to the right is 100% of your data. Okay, and this applies to any data that looks like this. The 68, 95, and 99.7 is going to be the same for every data that looks like this. Okay. Now, I'm going to add some more numbers here. So I know that 108 to 132 is 68%. What's the middle to 132? Okay, if I know 108 to 132 is 68, then 120, the middle to 132 should be half of that, right? So half of 68 is 34%. What about from the middle to 144? So middle to 2 up should be half of the 95%. So 95 divided by 2, 47.5. What about the middle to the 156? So middle to 156 should be half of the 99.7. So 99.7 divided by 2 is 49.85. And then what about the middle all the way to the right? So middle all the way to the right should be half of the 100%. So middle all the way to the right is going to be 50%. Okay, and then same thing to the left. Middle to the 108 should be 34%. Right? Middle to the 96 should be 47.5. Middle to 84 should be 49.85. And then middle all the way to the left should be 50%. Okay, so all of these questions in example 2, we're going to answer by staring at this picture. Okay, part A, B, and C should be pretty easy because they come directly from the picture. So part A says, what percent of 18-year-old women have systolic blood pressure between 96 and 144? So between 96 and 144, 95%. Approximately 68% of 18-year-old women have blood pressure between what two values? Well, 68% is between 108 and 132. So 108, and these are blood pressure. So blood pressure is measured in we said 132. I think that means millimeters mercury, I think. Part C, what percent of 18-year-old women have blood pressure between 84 and 156? 84, 156, that is 99.7%. Okay, so part A, B, and C involve just staring at the top part of the picture. Parts D, E, F, G, and H, these are now the harder questions. Part D says, what percentage of 18-year-old women have blood pressure above 132? Okay, above 132 means 132 all the way to the right. So I want this piece. So how would I get this piece? Well, I can get this piece by taking this 50% piece, right, which is too much, and then subtracting off this 34. So if I take the 50% minus the 34%, that should give me exactly this piece, which is what I want, 132 all the way to the right. Okay, that suggests that I should do 50% minus 34%. And 50% minus 34% is 16%. Okay, now let me kind of give you some tips here. So all of these questions, parts D, E, F, G, and H, are going to involve either adding or subtracting two of these numbers down here. Okay, so first of all, how do you decide which two numbers you need? So the way one way to think about it is, I want 132 all the way to the right. So I want this piece, right? Look at where these two edges are touching, right? So the 132 is touching the 34. Okay, so touching the 34. The right side, right, which is here, is touching the 50%. Okay, so that's telling me that my answer is going to involve the 50% and the 34%. Now, question is, do you add or do you subtract? So one way to think about it is the entire picture is 100%. Okay? that's 50%, right? Half the picture is 50%. So if I want 132 all the way to the right, that's that picture, which is less than 50%. So I expect my answer to be less than 50% for sure. Okay. So once you decide that it involves 50% and 34%, you're not going to add them, because if you add them, you get 84%. But we just said that that's definitely less than 50%. That's definitely not 84%, right? So that suggests that you should subtract. Okay, part E. Let's try another one. What percentage of women have blood pressure below 144? Okay, below 144 means 144 all the way to the left, so it's that piece. 144 all the way to the left. So the proper way to think about this is, I can think, so if I want 144 all the way to the left, I can take 144 to 120, which is 47.5, and then add 120 all the way to the left, which is 50%. So I'll take 47.5% and then add on the 50%, and that should give me my answer. Okay? Now, let's kind of go through the process that we did like on the previous part. So 144 all the way to the left. If I look at where my fingers are touching, right? So the left piece is touching the 50%. So I know it involves the 50%. My right side is touching the 47.5. So I do know that it should involve the 50% and the 47.5%. Okay? So let me write that down. And then the question is, do you add or do you subtract? So once again, think about, do you expect the answer to be big or small? Right? So 144 all the way to the left is this picture. Okay? That's a big chunk. I expect my answer to be big. Right? So that suggests that I should add. Because if I subtract, I'm going to get a really small number, which doesn't match what I expect the answer to be. So that's a suggestion that it should be addition here. Okay, and that's 97.5%. Okay. Part F. What percentage of 18-year-old women have blood pressure between 108 and 144? 108 to 144. Okay, my left piece, my left side is touching the 34, so I know it should involve 34. My right side is touching the 47.5. So I know it should involve the 34 and the 47.5. So this piece and this piece. Do you add or do you subtract? Okay, so hopefully by just looking at the picture, it's clear that you would add these two to get this piece. Okay, so I know, so left side's touching 34, right side's touching 47.5. So let me just write that down. 34, 47.5. Okay. Now, 108 to 144. That's 108 to 144. Okay. That's definitely not a small piece. Right? So I don't expect a small answer. I expect a kind of big answer. Right? So if you were to subtract, right, 47.5 minus 34, you'll get a small percent, which doesn't match the picture, or doesn't match what you expect the answer to be. Right? We do expect the answer to be kind of big. So we should add. So 34 plus 47.5 is 81.5. Part G. What percentage of 18-year-old women have blood pressure between 84 and 108? Okay, 84, 108. 84, 108. My left side is on the 99.85. My right side is on the 34. So I know it involves a 49.85. and a 34. So let me write those down. And we said 34. So we're doing 84 to 108. So I know it involves this piece and this piece. Hopefully you can see that to get this piece, you would take this piece, subtract off this piece, and that should give you exactly this piece, which is what you want. But let's think about this in terms of, do we want a small piece or do we want a big piece? So 84 to 108 is that. That's pretty small. So I do expect my answer to be small, right? Definitely less than 50% for sure, because 50% would be 120 all the way to the left. And if I want 84 to 108, that's definitely less than 50%, okay? If I add it, I'm going to get like 80% or more, right? So I definitely should not add, subtract. So 49.85 minus 34 is 15.85. Part H, what percentage of 18-year-old women have blood pressure between 144 and 156? 144, 156. 144 is on the 47.5. 156 is on the 49.85. Now, question is, do you add or do you subtract? Hopefully, by looking at the picture, you can see that to get this piece, you can take this piece, subtract off this piece, and it's going to give you that piece, that small piece that you want. But also think about it, 144 to 156, that's a really small piece, right? Definitely I should be subtracting, right? Because I'm expecting a really small answer. If we added those, you get like 90-something%. Definitely wrong, okay? So we said it should involve 47.5 and the 49.85. And because we're expecting a small piece, a small answer, we should subtract. So we're going to subtract. Now we should put the bigger number first. So 49.85 minus 47.5. And that is 2.35. All right, have a good day, and I'll talk to you guys later.